Right. Let me remind you first what we discussed in the last class about Hoffman bromomide degradation. This is a reaction where an amide on treatment with Br2 in the presence of NaOH is being converted into primary amines and Na2CO3 plus NaBr, 3 moles of NaBr, correct? Sorry, 1 mole of NaBr. So this is what will happen. Now, there are reactions which mimic or which have quite similarities to that of Hoffman bromomide degradation. Starting with first Curtius reaction. Curtius reaction is when you have an acid chloride reacting with sodium azide. This is an azide salt. Azide as a nucleophile will attack on this position and it will make us get into C double bond of N3. Now check the structure of it. Basically it is RC double bond O, N minus and N triple bond N plus. This entire thing is N3. Here we can clearly notice that N2 is a very good leaving group, and as it leaves, this negative charge will push here to make a double bond, and that's when R can substitute here. So same Wolff rearrangement will happen. That leads to the formation of Rn double bond C double bond O plus N2. What is this? This is isocyanate. And we learned that isocyanate on hydrolysis, H2O, will convert into RNH2 plus CO2. So it is the same reaction. We are getting the same products, but this time from acid chloride. Earlier we did that for amides. This time it is for acid chlorides. Another very similar reaction known as the Lawson's reaction. Here the reaction is C double bond O NHOH. Okay, so this is hydroxyl amide. This is an amide. So this is an hydroxylamide. Hydroxylamide, in case if it undergoes, if you treat this with TSCl first, I will get this as RC double bond O NHOTS. Now, in case if this has been treated in base, so we will get this as RC double bond O N minus, because this hydrogen is quite acidic, and this will be OTS. And you know that OTS is a very, very good leaving group. So I can use this point here that Wolff rearrangement can happen here. OTS can leave. R minus can attack here. This negative charge can close into double bond. And that converts into Rn double bond C double bond O, which is isocyanate. That isocyanate plus OTS minus TSO minus here. So that on further hydrolysis will finally give us RNH2. So again you get primary amine, but this time using hydroxylamine. Got it? Another similar reaction is Schmidt reaction. So DT here, Schmidt reaction. So Schmidt reaction is about making an carboxylic acid to react with N3H, which is hydrozoic acid. This is hydrozoic acid, and that on treatment in an acid, it will convert into RC double bond O, and here you will get N3. Okay, so imagine like this. I will give you the mechanism also here. So it is like we get this as OH2 plus first kind of protonation from hydrozoic acid, and then N3 minus will attack here and leave this group. On that way, we will get this as Rn3. Okay, Rn3 here. Sorry, Rc double bond O N3. And again, we learned this already that Rc double bond O N3 structure is like this: N minus N triple bond N with plus. This is the same thing we learned in Curtius reaction. So this will push, N2 will come out, R will attack. Okay, internally it will attack. So what do we get here now? Same R N double bond C double bond O and isocyanate plus N2. So this is an isocyanate form. Okay, so this isocyanate, correct, on hydrolysis will convert that into RNH2 plus CO2. Yeah. So same reaction, guys. So in total, we have four similar reactions. One is HBD, Hoffman bromamide degradation. The second one is Curtius reaction. Third one is Lawson's. Fourth one is Schmidt reaction. All of them does the same job. That is, there is a Wolff rearrangement for different cases. All okay? A lot of times name is not used in the questions because directly if you notice NCRT, they do not use the Curtius, Lawson's or Schmidt names as such. There is no names defined, but because the idea is the same, a similar mechanism question can be asked like that. Okay, next. We can get amines even from amides also. Okay, so suppose if you have to get reduced without loss of hydrogen. So this is without, sorry, without loss of carbon. So which means it is not a step down reaction as earlier how we learned. So for instance, if you have R C double bond O NH2, okay. If at all I take this compound and react with lithium aluminum hydride LAH, that will convert this into RCH2NH2. Okay. In case if you treat this with uh, red phosphorus, and HI, that will also convert into RCH2NH2. These two are typically used for making reduction reactions. Now, same thing I can do this time with NR2 also. If you have NR2, so same reduction would happen here. So this will become R2 here and R2 here. So everything converts into amides. Okay. Now, if you notice the number of moles here, if I take 2 moles of RC double bond O NH2, I would simply require 1 mole of lithium aluminum hydride. Okay, because lithium aluminum hydride provides 4 H minus groups. So I mean 2 will go to carbon and other 2 will go to oxygen. So that way it will convert into 2 moles of R C CH2. So you can see 2 here and another one is NH2. Clear? So 2 moles here. Acha, oxygen will take hydrogen from water. Okay. So that is not directly coming from here. So that will take it from water in the second step. But carbon will take 2 H minus. 1 mole will take 2 H minus. 2 moles will take 4 H minus. So that's how you will get 2 moles of amines. So the ratio in which they react is 2:1 ratio. 2:1 ratio to make the product. Okay. Right. Next, notice what are the generic reactions of acids. Acids, when you treat with acid chlorides, I mean SOCl2 to make acid chlorides, PCl5, CCl3, and POCl3. All of these, have only one thing to do. So they all will provide Cl minus. And that Cl minus eventually is replacing this OH minus and gets you through acid chloride product. Okay. All of these reactions are SN2 type or SN2 kind. What do you mean by SN2 kind? So it will be basically SN-TD mechanism. How does that work? If you have RC double bond O OH, okay. So first this oxygen will get connected with sulfur, double bond OCl here, gets a positive charge on it. And the rest other molecule of Cl will first connect. Directly removal will not happen. First an addition will take place. So I will get this as O minus O S double bond O Cl, and Cl got connected here. And now when the O minus will push this time, sorry, this is a hydrogen also here, plus. And this time bond breaking will take place, and we will get this as RC double bond OCl plus S double bond O, Cl and OH. Correct? Now do it for one more mole. You will get chlorine also out. Okay. So it is an SN2 kind of mechanism. Overall, it is an overall it is a substitution on the same position, but it would go through addition then elimination kind of reaction. Next, Hunts-Decker-Borodine reaction. Hunts-Decker-Borodine reaction is again a step down reaction where we are trying to remove the CO2 group from the acid and connect this R with, uh, alkyl halide, uh, with halogen to make it into alkyl halide. So let me write the overall reaction. See, first, when you take acid and react with a moist Ag2O, moist Ag2O is base. So OH minus will take away this H plus, and the RCO minus which is there, it will club with Ag plus and form a precipitate here. Now this we will heat it slowly. So this is where the mechanism starts. That is RC double bond O Ag. We add it to some uh, solvent, any non-polar solvent, and heat it with HBr2 or send light to it. So what do we get? Okay. First thing I will get this is RC double bond O. This O minus will make a bond with bromine to make Br plus, and silver will convert this into AgBr. AgBr precipitate. This will convert into AgBr precipitate. Now notice the second step here. The second step is this compound, right? In the presence of light or heat, will convert into radicals. That is RC double bond O dot plus Br dot. The third step is about, okay, RC double bond O dot. That will start, that is the rate determining step, which will convert into R dot and CO2. Okay. And now this R dot will again react with Br2 to propagate into RBr plus Br dot. So that's how you will get alkyl halide. Okay. So please check this out. This is the mechanism you guys need to know. Clear? Please check quickly. Just give me a second. Check. Next. If you have silver salt of this carboxylate and you treat with Br2, since it is a radical mechanism, even at the bridge position, the reaction will be successful. In case if it was a positive charge here, that means carbocation formation, you know that carbocation is not very stable on a bridge position. That's why in case of SN1 type of reaction, this reaction won't happen. But since it is a radical, the reaction could still take place, okay, on a non-planar carbon also. Correct? Now, in this topic, if there is any new reaction or very specific reaction, then I mean, there are only two reactions. One is Hoffman bromamide degradation, which I told you, and another one is this one, HVZ reaction, Hell Holhard Zelensky reaction. Okay. So the idea of this reaction is we are making an alpha halogenation on the acids. For example, if you have alpha halogen to be done, we first must have an alpha hydrogen present. That's the requirement, at least one alpha hydrogen. Thereafter, as you react with red phosphorus and pass it through, I mean, let X2 gas pass through this solution, you will notice slowly one of the hydrogen is replaced by halogen. So that will become alpha halo acid. Now, red phosphorus or PCl3, you can directly use red phosphorus plus X2, or we can directly use this as PCl3. This is required in a very small composition on a catalytic amount to make the reaction. Okay, so let's see the mechanism how it works here. So basically, we expect that phosphorus in Cl2, red phosphorus in Cl2, will convert this into Cl3. And we earlier learned that in case if you have an acid, COOH, and if you react with PCl3 or PCl5, in both the cases, we will get this as acid chloride. COCl will be formed. Okay. So this just happened via SN2 type of reaction. And RCH2, and then we have C double bond OCl. Keeping it for a long time, slowly it start tautomerizing. So this is a slow process to show itself into RCH double bond COH and Cl present here. Okay. So this is like an enol form. Got it? It is this enol form which reacts with the chlorine molecule. So lone pair from oxygen pushes here. The pi bond from here pushes onto any one of the chlorine and remove the other chlorine out. So as it does, right? So remove the Cl minus from here. So we will get this as RCH. One Cl will be present here, and then C double bond OH plus and Cl minus. The Cl minus which is released will be taking this H plus away and converting that into R CH Cl C double bond O Cl. Okay. So alpha halo acid chloride. Very important to learn that this is an intermediate form. Okay. Alpha chloro acid chloride is an intermediate. In fact, when you react with the second mole of RCH2 COOH, this is the second mole, okay? So this is the second mole. The first mole is here. This is the first mole which is reacted, and this is the second mole which we are reacting. After the second mole, now this reactant will convert into RCH Cl, and this will become COOH, while the second mole which is RCH2 RCH2 uh, COCl. This is a conversion that you will notice. It is honestly as if this OH is coming here and this Cl is replaced here. That's what is happening. In fact, there is a mechanism defined to it, but that is what is the overall reaction that takes place. Got it? And you can clearly notice that this is a slow process. And in the slow process, we are not doing any halogenation. The halogenation, in fact, is the second step. So since slow process or slow step is enolization, slow step is enolization, rate of halogenation remains same for whether it is chlorine, bromine, or iodine. Okay, whether it is chlorine, bromine, or iodine, that will be the rate. Got it? HVC has a lot of advantages, especially if you want to make proteins, amino acids, right? This is a very, very useful process. So let me show you how. First reaction set, HVZ based reaction. We have RCHCl reacting with aqueous ammonia. Now, as ammonia as a nucleophile, if it attacks here, chlorine can be released here, and you'll get this as, alpha amino acid. Okay. To be honest, if you notice the step here, so what might be happening is first RCH, correct? And this acid will convert into COO minus NH4 plus, and acid base reaction will take place. Okay. And then the second mole of ammonia would attack on it and remove this chlorine out, by which I will get this as RCH NH3 plus and C double bond O, you know, O minus NH2, NH4. Now this on slight heating will give us back as RCH, NH2, right? And this will become RC double bond O OH again, releasing back ammonia. Okay. So what do we get here is alpha amino acids. Okay. So that is what I have written it here. So you can see it will give you alpha amino acid. Second, in case if you use aqueous NaOH, first it will become CO minus, and the second mole will attack here, remove this chlorine, and thereafter you do hydrolysis, you'll get alpha hydroxy acid. Okay. If there was an R configuration here and you are treating with dilute aqueous NaOH, right? So that R, I mean, whether you take H2O or dilute aqueous NaOH, in both cases, you will notice that you will get R and S, but R will be major. Why NGP will happen? You know what is NGP? Neighboring group participation. That is, it is like we have chlorine here, correct? And the double bond O and OH of this acid, in turn O minus here, CO minus in basic medium. So it will be like O minus. In this basic medium, the lone pair of it will attack, Cl will be relieved. So it is H and R. So as it goes away, you will have a three-membered ring here, so which is oxygen with double bond here like this. Okay, with a plus charge and O minus. Correct. And now when the second mole of OH minus approaches, it will approach from the same direction from which the chlorine has left. So this is, an neighboring group participation where SN2 happens two times. So when you have two moles, I mean two times SN2 happening, sorry, two times SN2 happening, then the retention is observed. So you can see if this is R configured, the product will remain R configured. And if this was S, I mean the minor product will be only SN2 attack, which will be from the backside. Okay. If you just check out the last step of HVZ, I just wrote down earlier how the conversion takes place. But if you notice clearly what is happening here is the second mole of acid will attack on this as an addition. So after the addition has taken place, correct? So lone pair from here will push it, pi bond will push it here. So you will get this product form. And because this OH plus will try to be more stable, this O minus will break into double bond, remove out this chlorine. And as the chlorine leaves, that chlorine internally will attack C double bond O. So complete replacement, replacement will happen. Now notice this is a product which is formed, right? That is used as a reflux. Okay. So this is product, and this is a reflux. Reflux as in, again it is sent back to the compound in the same reaction. So C double bond O Cl, and that when you react with X2, right? that will convert into R CH X C double bond O Cl plus HX. Correct? This is how the reaction will keep happening. And that's the reason why I told you that only an electrophilic, I mean, a small catalytic amount is required for making this reaction. Okay. So this is all the information you need to learn from HVZ reaction, everybody. Now let's get to the next point. Whether carboxylic acids can give uh, aromatic substitution or not. Okay, you see, CO minus when you react with concentrated HNO3 and concentrated H2SO4. So it will always give you meta product more than anything. Okay, meta product more than anything else. Got it? And second, I think this side of the reaction is not correct. I had to correct that. Let me show you. By chance, if you are subject to basic medium here, in the case of basic medium, now you see anything which is this will convert into COO minus, and CO minus is again ortho para directing. In fact, some amount of meta will also come in this case. So if you react with this one, the ring will get activated ring. So activated ring would give you orthopera directly. And that's what happens here. You can see iron in Cl2 if you add it down. So it will convert that into CO minus and ortho product Cl and para product will come across. Okay. So there is not much of EAS reactions, only this. Okay. Next. What is a test for carboxylic acid? See, if you react with sodium metal, it will give you a hydrogen gas. Litmus test, it will convert blue to red color, blue litmus paper to red color. Sodium bicarbonate test, it will give brisk efflorescence of carbon dioxide. Alcohol test, which means if you add alcohol, it will convert into ester, and esters are fruity smelled vapors. Mercury chloride set, it is only observed in the case of formic acid, only formic acid. If you treat with HgCl2, it will become HgCl2 white with HCl and CO2. FeCl3, okay. Generally, for carboxylic acids, when you react with FeCl3, it will convert into red coloration of the liquid. So, which is FeCl2 and OORCOOR minus. Okay. Got it? And lastly, KMNO4 test. That means this is again observed for formic acid and oxalic acid. By chance, if I take formic acid, 5 moles of formic acid react with KMNO4 and H2SO4. KMNO4 can reduce to MnSO4. Formic acid will get oxidized to CO2. So initially it was purple color. Now it will convert into colorless solution. So KMNO4 is also used as a test when it comes to carboxylic acids. But which carboxylic acids? Only formic and oxalic acids. All okay, guys? So this is what you need to learn from carboxylic acids. Okay. Let me take you through some derivatives of carboxylic acids. So starting with ester. Ester is the only important derivative. Let us spend some time on esters. See, methyl methanoate is the name that we use it for esters. This one. Whatever the R present here, without any numbering, we have to write it first. And the suffix for esters is O8. So that will become methane and O8. Here this is isopropyl 1, 2, 3. So it will become propanoate. Isopropyl and propanoate. What about this one? This will become ethyl pentane. Okay. Ethyl pentane 1, 5 dioate. Dioate. Because O8 is on both sides. And we don't need to mention the numbers because ethyl will be on them only. But if you have two different cases, right? Okay. So in that case, we will represent it as, 1 dash ethyl, 1 dash ethyl and 6 dash methyl. 6 dash methyl, and then we have hexane, methyl hexane, and 1 comma 6 dioate, 1 comma 6 dioate. Next, here this is also ethyl and cyclohexane, complete name, and then CO minus, that becomes carboxylate, that will become carboxylate. Next, here also we have ethyl, so two ethyl, so diethyl malonate, because it is coming from malic acid, it is usually called as malonate. DEM, dimethyl malonate, diethyl malonate. Okay, done. See the preparation. Esters, we learned the preparation in alcohols, that is esterification. Acids and alcohols, when they combine with each other in acidic medium, it will convert into ester. Okay, and this ester formation is called Fischer esterification. What if I take diazomethane, CH2N2? CH2 minus will react with H plus. You'll get RCO minus. Now N2 has become a good leaving group. So CO minus will connect back and you'll get this as esters, methyl esters. So if you want any methyl esters, diazomethane is a good way of doing it. Next we have MCPBA, which is Baeyer vinegar oxidation. Baeyer vinegar oxidation suggests that, depending on the migrating aptitude, if you use that in the presence of peroxy acids, right, any one of the side oxygen will get connected. Now on which side it will get connected depending upon the migrating aptitude here. Okay, so what is the migrating aptitude of these compounds? You can see first it is 3 degree, and then we have cyclohexyl, 3 degree, and cyclohexyl, then 2 degree, then we have phenyl, 1 degree, and methyl. This is the order of migrating aptitude. Okay, next. In case if you have esters, you react with alcohols, you'll get new esters. Sorry, if you have anhydrides, you react with alcohols, you'll get new esters. Okay, ester and acid. Acid chloride also, if you react with alcohols, you'll get into esters. Ketenes, when you react with alcohols, you'll get esters. So these are all, different combinations to make esters. We learned Tischenko also in aldehydes ketones, where if you have an aldehyde, you can imagine as if it is going to a Canizero. If it goes through Canizero, one will be acid, one will be alcohol. Combine both of them to form esters. So that is Tischenko reaction. Okay. Next, if you have carbonate RCO minus reacting with RX, CO minus will also act like a nucleophile attack here and convert into an ester form. So please check it out quickly. These are all the ways of generating esters here. Okay. Okay. Next, check out what are all the properties of esters. See, esters are generally fruit smelling compounds. Fruity smelling compounds. It has high volatility due to lack of hydrogen bonding. Okay. General reaction of esters. Esters usually give only one type of reaction, that is nucleophilic substitution, where you have O minus, and if a nucleophile Z with a lone pair is connected here, this will rearrange and it will form RCO minus, OR dash, and Z. And now when this O minus closes, this RO minus will come out. This type of mechanism is called as SNTD. So it is not direct substitution, it is First an addition followed by elimination. So through SNTD, you'll get this as R C double bond O Z plus RO minus. Now this Z could be anything. It could be OH minus. It could be NH2 minus. Even simple NH3 also. Okay, it can replace it. All right. Next, this is an important area for this topic for esters. That is hydrolysis of esters. Okay, that means if we take esters, esters can be hydrolyzed back to acids and alcohols. And usually we can use, most of time we use acidic medium, but even basic medium does the same thing. Now remember one thing, guys. If you want to make esters, right, it is only possible in acidic medium. Okay, but if you want to hydrolyze esters, it is possible in acidic medium as well as basic medium. Okay, now while making the acid and alcohol back, you got to break this bond, correct? Now there are two ways to break the bond. One between carbon and oxygen here, or acyl carbon and oxygen. The other side bond breaking is alkyl carbon and oxygen. So since you are breaking an acyl bond here, you call it as an acyl cleavage, acyl oxygen cleavage. And the abbreviation that we use is AC, acyl. If the cleavage is happening between R and O, right, alkyl and oxygen, we call it as alkyl oxygen cleavage. We call it as AL. We call this as AL. Now, there are many types of mechanisms here. Correct. So first one, let us start with case one, where I'm making a reaction like this. R C double bond O O R dash is present, and on protonation, the lone pair from this oxygen, okay, will connect onto proton here. So that will convert into R C double bond OH plus and OR dash. This is what we have. Okay. And now it is the water which will attack as a nucleophile towards this carbon to open it up. So like an SNTD reaction. So you will get this as R, C, OH, OR dash, and here we have OH2 plus. Okay. Now from here, the hydrogen will get migrated. That is IMPT will happen. So we'll get this as RCOH, and this will get the hydrogen here on plus charge and R dash and another OH group here. Right. So now OH2 is a good leaving group. So the lone pair from this oxygen will push and try to remove this molecule out. So by doing that, what do we get? I'll get this as RC double bond OH plus and OH plus R dash OH. So this is how the esterification works. Okay. Now notice something. Where is the bond breaking happening? So if you notice that the bond is breaking between carbon and oxygen. So it is a acyl cleavage, right? So we are noticing an acyl cleavage here. Since it is an acyl cleavage, the type of mechanism is called as mechanism is called as AAC twice. AAC twice. Why? The rate determining step is always the, rate determining step is always the addition of nucleophile. Correct. So during the rate determining step, how many molecules were involved? Two molecules were involved. One is this one, the other one is this one. That's why it is AC twice. And since there is an acyl cleavage, we use the word AC, and it is happening in an acidic medium, so you call it as A. So AC twice. That is the type of mechanism. Clear? See the second case now. The second case is when you have an ester RC double bond O R dash. This is the ester we have, and this ester is subject to acidic medium H plus. I'll get this as RC double bond O, you know, OH plus, and we have OR dash. Okay. Now, IMPT could happen. You'll get this as RC double bond O and R dash. And that hydrogen will be appeared here with a plus charge. Right. So we'll get this as after the removal of this RMPT. Now here is the decision making, guys. What if this R dash is very, very stable due to its carbocation nature? If it is very stable, chances are that oxygen can break on this end also. If it happens to break like this, right, like that, it will become RCOOH and R dash plus. So forms only for stable carbocation. So it will go as stable carbocation. So therefore, this type of mechanism, mechanism is called, sorry, acid catalyzed Al, and now the rate determining step is important. Which is the rate determining step here? Okay, because water has not attached on this position here, correct? So this is the rate determining step. Hence, during the rate determining step, only one molecule is involved. Hence, Al1. So this will be Al1. AAL1. So remember this, we learned two types of mechanisms. One is AAL1, the other one is AAC twice. One is an alkyl cleavage, the other one is an acyl cleavage. Please check. If you have any doubt, you can ask me now. Check out hydrolysis in base acidic medium. In case of base catalyzed mechanism, so let's see the basic case here now. Suppose I have C double bond O R dash, and I'm directly treating that with OH minus. OH minus directly attacks here, get an addition form. So that will convert into RCO minus, and we have OR dash and OH. This is what you will have, and that will be in equilibrium, correct? Sorry, yeah. And now O minus will push it here, and RO minus will come out, which will make it as RC double bond OH plus RO minus. Here is interesting part. This step is completely non-reversible. Reason being, RO minus is a very strong base. It can take H plus from this acid, and it will convert into RC double bond O minus. And then you will get this as ROH. Earlier in acidic medium mechanism, all those steps are reversible, which means acid and alcohol which are formed, they can again resume back the reaction towards ester. But you will not find a reaction where we have an acid ion reacting with an water, because acid ion is very, very stable due to resonance. So it does not react directly here. Now, in this case, again, breaking of, uh, you need to check out what is the slow process. The OH minus, which is present here, I mean, that is the rate determining step or slow step here. So you can see in the slow step what is involved. In the slow step, if you get the I mean, the name of the reaction here. So if you notice, we have, an basic medium used, correct, which is a bimolecular reaction. There are two molecules used during the RDS, and there is an acyl cleavage after that. Okay. So since there is an acyl cleavage here, so what do we call here? This is BAC twice. This is the form which you need to know. So basic medium, acyl cleavage, and bimolecular step. In fact, when it comes to basic medium, you will hardly see other forms. This is the only form which is to be learned, and that is the only one which you have it in the syllabus also. Got it? And this comes with very famous reactions if you could recall. That is, I have CHO, CO, C17, H35. Similarly, CH2 here, CHO, CO, C17, H35, CH2, one second, CH2, O, CO, C17, H35. These are triglycerides. Triglycerides. Triglycerides, when you react with NaOH, okay, it is a irreversible reaction where you'll get 3 moles of C17, H35, COO minus Na plus, which you call it as sodium stearate. Sodium stearate is nothing but the soap which has been, I mean, this is the typical composition of the soap. And we will get another product which is glycerol. In fact, this method is employed for preparation of glycerol, or glycerine. Got it? So this is also an irreversible reaction, guys. And since it is preparation of a soap here, the reaction's name is called saponification. It's called saponification. Clear? So this is what we need to know it from basic medium. Okay. When do we typically get AAC2 type of reactions? When both side of the R, you have both side of the R, they are very simple groups. That means they are not very bulky, something like methyl, ethyl, propyl type of groups. Second, if you have AAL type of reactions, okay, that is the second one which we saw that here, second case, AAL1. AAL1 is observed when this R dash is only bulkier. That is bulkier so that it can become stable carbocation. So in case if it becomes a stable carbocation, then this mechanism must be employed. For example, if you have CH3, C double bond O, and this is connected with 3 methyl groups here, like this. Okay. In such case, if you hydrolyze it, then what do we get? We will get this as CH3, COOH. Okay. Imagine this is 18. So that 18 will retain here. Okay. And the second product, what you will get is alcohol. So the mechanism type here is acid catalyzed alkyl cleavage with unimolecular reaction. Next one is AAC1, very rarely observed, but it is mainly seen when you have R group being very bulky, or it is 3 degree where it can become a stable carbocation. So let me show with an example. Suppose I have like this C double bond O, OCH3, that on hydrolysis H3O plus. Okay, then we will get this as COH plus and OCH3. Got it? And this will get into an intramolecular proton transfer and get this as C double bond O, OH plus CH3. Okay, just a second. Right, sorry, check. So if you get this, now you know that this is a stable molecule here. So this will break here first. So as it breaks, this is an acyl cleavage, and then you get C double bond O plus and CH3OH. Okay. And thereafter, if you compare this one here, this becomes an unstable carbocation before even water get to attack here. Reason being, it will immediately dissociate itself into give a very stable gas, which is carbon monoxide. And that is happening because the next incoming carbocation is a very stable carbocation. So from here, now when the hydrolysis happens, you'll get this as alcohol. So overall in the product, you actually don't see much of an acid. You'll only see uh, you only see alcohol. Correct? So this is AAC1 type. In fact, of course, this could be this could be major or minor. We can't say that, but some part of it before getting departed also, you will see C double bond O plus can get hydrolyzed, and that can give you acid C double bond O OH. So what are the products that you will report? One product is this one, an acid. The other product is this one, an alcohol, which are most generic one. The other product is that acid derivative has been uh, disproportionated to get this product. So these three are the products you will show. This is AAC1 type of reactions. Okay. So a lot of questions you will see even in MS Shawan or different sources. All these examples have been given. So left hand side bulky, right hand side bulky. Both sides it is normal. In all of these cases, if it is acidic medium or a basic medium, you should know what to do. Next, rate of reaction depends upon withdrawing nature of the group also. In case if you have a stronger withdrawing group, the rate of reaction would happen faster, specifically in the case of basic medium. So therefore, rate in this case, if these are the groups, I would say NO2 would make a faster reaction than Cl, then H, then CH3, and then OCH3. Okay. The product in this case would be simply carboxylate, which is COO minus with a group G plus ETOH. This is the product. Okay. Next. See, next reaction is ammonolysis. That is we can notice that ammonia can actually replace this RO minus easily because ammonia is a relatively stronger base compared to what, in fact, the product formation is amide. Amide is a very stable product compared to esters. That's the reason why ammonia can be deployed here and remove RO minus. Okay. So mechanism type is very similar. That is, in case if you have R, C double bond O, O R dash, ammonia as a nucleophile will attack here. Addition will take place. You get this as R, C, O minus, NH3 plus with O R dash. Okay. And that will make it as R, C, O minus, and we'll get this as, sorry, OH, and here we get this as O R dash, and then NH2. Okay. So the lone pair from here will push to remove out this OR minus. So that converts into, sorry, from here. Lone pair from here will push to convert into RO minus. So we'll get this as OH plus and NH2 plus RO minus. And that RO minus will take the H plus and convert into RC double bond O NH2 plus ROH. So this is a final product. This is how the ammonolysis works. Okay. Let me give you one example which was asked in GE. So a diester was asked like this: double bond O, OET, double bond O, OET here. And this was reacted with methylamine in excess. So first, what do we get here is an amide form, double bond O, NH and Me, double bond O, NH and Me. This is what you will get. And this on strong heating, correct? This ammonia can also attack internally and convert this into an imide form, methyl, double bond O, double bond O, and Me, NH2. This is the product. So what is this one? N-methyl phthalimide. N-methyl phthalimide. Okay, this will be asked. Okay, what is N-methyl phthalimide? How is it prepared? So please do check. Second, if you have internal attack, that is OMe here and NH2. Internally, nitrogen is present, which will act like a nucleophile to attack here. And then, of course, this group will be left eventually. So ring size is 1, 2, 3, 4, 5, 6. So with a 6-membered ring, we need to have an amide form like this, cyclic amide and MEOH. Cyclic amides are called lactams. So this is alpha, beta, gamma, delta. So it is connected from delta. So it is delta lactam. Okay. This is called ammonolysis. Internally, SN2 is happening. Second, transesterification. That is, one ester is trying to generate another ester. So this is already an ester. If I take it into 1:8 ratio, then minimum is 1:8 ratio so that this alcohol can come here and replace this alcohol. So one alcohol replacing the other alcohol. That's it. For example, if you have reactant like this, O double bond lone pair here, and then I have R C double bond O OMe here. Okay. Now you know that this oxygen will push here, the pi bond will go and attack here, and that's how the addition reaction will take place. So now you will get this as RCO minus, which I will write it as OH here, and then we have OMe connected with this carbon here, okay, which is a six-membered ring, okay. But across that six-membered ring, we also have an oxygen connected like this with a double bond and plus charge, okay. Double bond and plus charge here. Just a second. Mm, right. So check it out. We got this as O here with a positive charge. And now what will happen is this lone pair would push here. This bond, I mean this OMe will go here, correct? And that will make it into RC double bond O, you know, with this compound present like this, with double bond O like this with plus here, okay. And then we have CH3OH form, correct? And the same CH3OH which is released will attack here so that the pi bond can be relieved. And that's how we will get this into R C double bond O, and we will get this as oxygen with OCH3. This is the product formation. So what is this one? An acetal formation. You can see an acetal formation. So you can see first we replace that, oxygen here. And this is the way we have made the reaction. And eventually it got an acetal form. Right. Next, see what are the other generic reactions here. So first starting with esters. Ester, when you react with PCl5, acid chloride, here also acid chloride, here also acid chloride. And CH3OH, CH3OH, CH3OH is separated and rest of the compounds will come across. Similarly, if you see the reduction reactions, that is, in case of ester, esters does not respond to H2 and nickel. They will respond to lithium aluminum hydride gets reduced. With NaBH4, no reduction. LiBH4 is made out of NaBH4 just to ensure that esters are reduced. Next, dibal H will convert into aldehyde and one part will be alcohol. This part will be alcohol. B2H6 has no reaction. Sodium and ethanol will also give you same reaction as lithium aluminum hydride. Okay. Now again, this was a JE question. Please check it out. That in case if you have COOH and COOET, what does B2H6 does? Okay. So check out what it can do is first we will get uh, carbon here, right? So that will convert into an alcohol. Okay. While here, if you notice from this end, we will not get disturbed with the esters. Okay. But what if I have hydrolysis being done first? H3O plus. On hydrolysis, we will get this as COOH. And suppose heat is also given, which means I'm expecting this to make a hydrolysis. And thereafter, a trans esterification. That means internally the other alcohol will connect. Okay. So trans esterification will take place here. So we'll get O with double bond O like this plus ETOH. So this is a product that you will report. So first reaction is with B2H6, second reaction is with hydrolysis and heat, you will get trans-esterification. Suppose these both reactions were given, that is, what if this was treated with lithium aluminum hydride? In that case, we will get this as an alcohol. Here also we got an extra alcohol, correct? OH and this group. That's it. These two are the products formed. Clear? So how it behaves with hydrolysis, how it behaves with lithium aluminum hydride. Okay, is what we need to know. In fact, in case if you take this acid, react directly with lithium aluminum hydride, okay, without making any reaction here. What if you directly react with lithium aluminum hydride? Even then you will get this one. Okay. Now, now let's understand the next important reaction of esters, that is, Claisen condensation. Sorry, check. So what is Claysen's condensation, everybody? Claysen's condensation is making an esters, to get coupling. Make basically an esters getting aldol condensation, aldol type of condensation. So that will give you beta keto ester. Okay. First, let me show the mechanism. It is very similar to that of aldol. So first mole, let's say the first mole, if you notice, it is about CH3 COOET. And that when you react with ETO minus, ETO minus will take H plus from here, converts into CH2 minus, so COOET. It is just like enolate ion, the carbanion which is formed. This is the first step. So this will be enolate ion. Okay, enolate ion. So this enolate ion, when you treat with CH3, C double bond O, OET, as you react, so you will get this CO minus, CH2 minus attacking here. OET will be relieved out. Okay. In that case, this is the rate determining step. It follows SNTD mechanism. In fact, first I'll show the SNTD mechanism. SNTD mechanism where we are pushing this pi towards oxygen. So what do we get here is CH3 CO minus OET, and this group got connected CH2 COOET. Okay. So the attack of this nucleophile is the rate determining step. Okay. Right. Now, once you get this form, you can see this O minus will push down and remove this OET from here. So as it leaves, so we will get this as CH3 C double bond O CH2 COOET plus ETO minus. So what did we get here? This is beta keto ester. This is how we get beta keto ester form. All right. So please go through it quickly. Give me a minute's time. Yeah. So I'm sure you must have understood how the Claisen condensation works, right? So it's same as aldol. Of course, there is no elimination part here. The elimination is like a substitution case here, right? So that's the whole idea here. So now let me show you some examples. Suppose uh, if you have this part, yeah, if you have any reaction like this, we have COOET here and treating with ETO minus and heat first, and then second, followed by hydrolysis. Second one is followed by hydrolysis in acidic medium. Now, what does this mean? Followed by hydrolysis, sorry, and also followed by heat. Now, what does this mean? So, if I take 2 moles, first let me write down what is the product. That is the product is like C double bond O, and then we know that this OET is been replaced by the second mole from the alpha position. So, we will have a methyl here, and this will be like CHCOOET with a methyl group on it. So, this is the compound that we have, correct? But now, basically, this on hydrolysis will give you this esters to get hydrolyzed. So we will get C double bond O, CH, CH3, and that will become COOH plus ETOH. Correct? And lastly, you know that this is a beta keto acid now. This is beta keto acid. So we already learned the fact that whenever you have a beta keto acid on heating, decarboxylation will take place. So we'll get this as C double bond O, CH2 and CH3 plus CO2. So this is the products that you need to report. So what are all the products you will report? You'll report one as ethanol and the other one as this compound which is ketone, and one more product is carbon dioxide. These are the final products after the overall reaction. Done. This is an important application here. Secondly, in case, another example, check out, in case if you have, very bulky kind of a substrate here, and then I'm treating this with ETO minus. Okay, this reaction does not make condensation. Reason being, the carb anion which is getting here is highly unstable. Okay, it is a very strong base. So it is not easy to make this strong base initially to make Claisen condensation. But you just need to make this reaction by changing the base itself. Okay. So instead of ETO minus, if at all I take a base here, B minus, strong base, this is a strong base. In that case, the reaction will work. So in that case, we will get, this will become COOET with minus charge here, and that will attack on the second mole of COOET. So from this minus point, it will attack here. This OET will come out here. So from there, we will get the product as C double bond O with C methyl and COOET. This is the product what you will get. So this is also a beta keto ester. But what are those strong bases, guys? The strong bases here includes pH thrice C minus, very strong base, KH or NaH, potassium hydride, or this one, or RLI, right? These are all very, very strong bases. Only when you take such strong bases, this reaction will be observed. Clear? This is about Claisen condensation. Now let's talk about cross Claisen condensation. Just like cross aldol, here it is cross Claisen condensation. So that is, we have two different sorts of esters. So then what are all the products you can expect? So first let me write down the self one. The self one, the first self one is CH3, C double bond O, CH2, COOET. This is the self of the first one. Correct? Now let me write the self of the second one, CH3, CH2, and then C double bond O and CH, CH3, COOET. This is the self of second one. Now the cross CH3, C double bond O, and attack is happening from this CH2 to this position. So we'll have CH, CH3, COOET, and the last cross product CH3, CH2, C double bond O, CH2 COOET. This is the cross product. Now, first compound does not have any chiral center, so you'll report only one. Here there is a chiral center, so you report two. Here there is a chiral center, you will report two. Here there is no chiral center, so we'll report it as one. So total six products are formed in this case. Got it? This is cross collision. Just like intramolecular aldol. Here we can also have intramolecular collision condensation. So we can see we have first, second, third, fourth, fifth, sixth position. So from here, this CH2 minus CH minus can attack here, convert into cyclization here this way. Okay. Here also you can see COET at the alpha position of this COET, we have CH2 minus. So this is also like a cross intramolecular collision. So from here the attack would happen, and this is the product what you will get. Okay, this is intramolecular collision. Next, FeCl3 test for esters. That is, in case if at all we have Fe plus 3 with any phenolic group, we know that it will give violet coloration. Okay, it will give you violet coloration here. Okay, so this one I wrote it a little wrong. Once again, let me correct that. Yeah, here. Correct. So now, usually, even if you have like 10% of enol also, you will see the product responding towards the color. That is, if you have like, beta diketones or beta dialdehydes, large quantity will be present in enol form. Enol form will form complexes with iron, giving different colors. While keto, when you have beta keto acids, this is beta keto esters. Beta keto esters will have some amount of enol content, which will also give you some colored colored complexes. But this is not as good as that of beta keto. I mean, beta diketones or beta dialdehydes. But still, you will see some colored formation observed from Fe plus 3. Okay. Now, how examples are being framed, and the overall reaction cases. Let me write two examples here and explain. For instance, if you have this is C double bond O O A T. This is a beta keto ester which is generated through the mechanism, and it has been further heated with ETO minus. In that case, you know that this is an active methylene group. So from an active methylene group, it will fetch H plus, and then we will get that minus charge on that position, OET minus here, and that minus will react with ETBr. So this minus would attack on ethyl, bromide will come out, and it will make the product as double bond O, double bond O, OET, and ethyl getting substituted here. And thereafter, correct, H3O plus is being done usually, which means ester will undergo hydrolysis, converts into an acid form, plus ETOH. And then it has been further continued with heating. So on heating, decarboxylation will take place. So we will get, ethyl here like this plus CO2. So this is the final product that we need to report, a keto product. So this is a very standard sequence of questions that will be asked. So first it will be asked to make a Claisen condensation, and thereafter again ETO minus reaction followed by ETBR followed by hydrolysis followed by heat. So this sequence is a very standard J sequence. Okay, so learn that carefully. Okay, guys. Okay, same question. See, if at all, I use the same reactant again, like this: double bond O, double bond O, OET. Okay, so if ETO minus, or just on one arrow, sometimes it will be mentioned like this: So first ETO minus. Second we have pH CH2Cl. Third we have ETO minus. Fourth we have CH3Cl. Fifth we have hydrolysis. And sixth we have heating. Okay, this is the way the questions would be given. So you can see first when you react ETO minus, the minus charge will come, it will attach here. Again I'm using ETO minus, one more time minus charge will come, again this will attach here. So I will write that intermediate forms here. So double bond O, one will be methyl, one will be benzyl, like this, with O eating. Thereafter, on hydrolysis, we will get this as an acid here, like this, with pH. And that on heating, strong heating, will give you pH here and CO2. So this is a final product that you are expected to report. Done? Got it? Similar line of reaction, one more, if at all I give you, I'll directly write the products here. So double bond O, double bond O, OET. Okay. So this is how it is being given. Sorry, this way. So first one is ETO minus, followed by CH3Cl, followed by NaH. This time instead of ETO minus, it is being given as NaH, followed by CH3Cl again, followed by hydrolysis, followed by heating. Correct? Notice the same sequence. So this is what you get as the product. So answer is, what is the product form? Simple product form is like this, plus CO2. That's it. This is the product form. Done? Any doubt? Done. Check. The next mechanism is acyl ON condensation. That is, an ester, when you react with sodium and xylene, followed by hydrolysis, will give you alpha hydroxy ketones. See, let's notice the mechanism. How does it happen? So first step of the mechanism is sodium releasing electrons in xylene. Okay. And then once again, sorry, check. So first sodium will release the electrons. So then we have R, C double bond O, O, R dash, 2 moles. Now imagine I made 2 moles to attack here. So what do I get? Is 2 moles of R, C, O minus dot and O, R dash. Okay. And these two radicals will get terminated. O minus dot, sorry, dot and O, R dash plus C dot O minus R and O R dash. These two will get terminated. So as they get terminated, I'll get this as C to C connection, O minus, O minus, O R dash, O R dash, and R. Okay. And now this will close into double bond, removing out this esters form. So that will give us R C double bond O, C double bond O, R plus 2 moles of RO minus. Okay, so this is a different way of coupling. We coupled such a way that both the OR minus groups will go away. Okay, and as you do hydrolysis here now, see the interesting part. Uh, correct, sorry. As you react with sodium again, as you react with sodium again, see the interesting part. You will get this as minus O minus. Again, two electrons has been added, and this time the electrons will terminate internally, making into a double bond form. And as you hydrolyze this part, we will get this as R COH, COH, and R. So this will undergo tautomerism, making one of the compound to get converted into ketone, other will remain into alcohol. So therefore, this alpha hydroxy ketone is what we call it as acyloin. Correct? So this is the product formation. If you may recall, this is a very similar reaction as a benzoin condensation. That's why the word acyloin, benzoin, these are similar terms. It is very similar to that benzoin condensation. Right? So please check once. All okay, guys? Check. Last thing, this is the product that you can see. So both sides we have esters, sodium and xylene, and hydrolysis if you do. What is the easy way to remember? Basically, we need to connect this carbon and this carbon and make them into acyloin form. So check out what is the ring size: 1, 2, 3, 4, 5, 6. So that's why I made a 6-membered ring. So one carbon you make it as ketone, one you make it as OH. So that is the acyloin intramolecular. Got it? Here, everybody. Right. Now that's it. This is how much we need to know. This is an extra information. Amides and acid chlorides, we have learned this before. What is phenolphthalein, how the reaction works. You can just go through it once. Okay, there is nothing much to teach here. Clear? So you guys can go through it. So this is how much you need to learn from this topic, everybody. Okay, acids not very major reactions are repetitive. The three main reactions that you need to learn: HBD, okay, that is Hoffman bromomide degradation; HVZ, okay, Hell-Hollard-Zelinsky reaction. Third one is Claisen condensation. Literally, these three are the only new reactions here. Okay, acyloin is just a borderline syllabus. It is not usually asked, but mainly in the syllabus, the reactions, if you ask me, only these three. These three you have to learn thoroughly. The rest, all of the reactions are repeat ones. Okay. So, as in when you finish the aldehydes and ketones, start working on carboxylic acids as well. Got it? Uh, I'll I'll try to wind up amines also in the next week. Correct. So amines and thereafter biomolecules. These are very small topics. We'll complete those topics in the next week. Okay.